Hi everyone. After a long delay, which I do apologize for, we're finally getting to this lever experiment, specifically looking at the case where I have a horizontal lever, and I hit that horizontal lever with a mass m1 going at some initial velocity v0 at a certain distance from the fulcrum, and when that mass hits, it's going to launch a second mass at the other end of the lever, and we want to look at different setups saying when I have different masses hitting at different distances, either sticking to the lever or bouncing off the lever, what we want to do in this video is experimentally demonstrate what happens in these different cases and identify what are the key physical principles that come into play. Now, in a previous video, which I'll provide a link for, I went through the details of what standard physics textbooks would say should be coming into play. And I just want to briefly revisit a couple of those points that are going to be of key importance when we're actually evaluating the data itself and seeing what we're specifically looking for. So, when we look at this in terms of linear momentum is not going to be conserved because the total linear momentum is only conserved when there are no external forces, and there is necessarily going to be a force at the fulcrum point when that mass hits, otherwise the entire bar would just be knocked out of the way. So we do not expect the linear momentum to be conserved. And even more to the point, in terms of linear momentum, we've identified in previous videos that linear momentum depends on direction. This mass m1, well, when it hits the bar, it's going to slow down. So not only is it losing some of its momentum, mass 2 is going to have a momentum going in completely the opposite direction. So we do not expect linear momentum to be conserved. However, when we look at angular momentum, the total angular momentum of a system is going to be conserved if there are no external torques acting around the axis about which we're measuring that total angular momentum. So when we pick this fulcrum as our axis point, we're going to make sure that it's very low friction, and then everything else that's hitting it, all of those would produce internal torques. So the total angular momentum of this system should be conserved, and that's going to be the key thing that we're testing out in this video. Briefly, to calculate angular momentum, if I just have a single point particle, it's going to be how far is it from the fulcrum point that we're using, times the mass, times the velocity. At least in this case, we're not worrying about it hitting at some oblique angle or something like that. So we can use that to calculate the angular momentum of the point particles. And for an extended object like the bar itself, as it rotates, that's going to be its moment of inertia times the angular velocity. So before the hit, mass 1 would have an angular momentum around this axis of r1 times m1 times v0. Afterwards, we've got the angular momentum of object 1, object 2, and the bar. And this is what I, again, really want to emphasize. This angular momentum should be conserved no matter what kind of collision we have. As long as there are no external torques, this total angular momentum should be conserved. Doesn't matter if the bar has some flex to it, doesn't matter if the masses hit and stick to the bar, doesn't matter if the masses hit and bounce off. Whatever the situation, as long as there are no external torques, which we should be able to manage to a pretty good accuracy, the total angular momentum should be the same. So I'm not going to go over the whole last video, but just a couple of the cases. In the inelastic case, if we have everything sticking to the bar, so m1 sticks to the lever and m2 is launched with a velocity matching the tangential velocity of the bar, then in this case, we can calculate what the velocity after the collision of both object 1 and object 2 should be. Again, it's a bit of an involved calculation. I show more details in the other video. And in the elastic case, let's say I have a case where when the object hits, it's going to bounce more. Well, if we get this m1 bouncing elastically and m2 launch with the velocity of the bar and no flex in the bar, we'll see if we actually get these matching up. then in this case, we're still going to get conservation of angular momentum, but we're also going to get conservation of the kinetic energy. And if you take those equations, you get this really ugly looking set of equations that, again, predicts how fast should object 1 be moving after the collision, and how fast should object 2 be moving after the collision. So, obviously, there are a lot of different quantities that are going to have to be calculated in here. And we're going to have to keep track of each trial. Is the angular momentum being conserved? And if we have an elastic collision, is the kinetic energy being conserved? Are we having a case where we're actually violating conservation of energy and getting more energy out than we started with? We want to be able to keep track of all those calculations. So to do that, I made this Excel sheet, and I know this looks ugly at first. But what we can basically do with this is, in this part over here, we can identify what masses are we using, and where are those masses hitting the bar, what's the moment of inertia of the bar. Okay. And then in these, we get the computer to calculate for us what is the prediction based on these equations that I've shown over here. What is the prediction for how fast object 1 and object 2 should be moving for the elastic case, and for the inelastic case, how fast should objects 1 and 2 be moving. And then we're going to be able to say, well, when I actually measure these values, what was the actual measured initial velocity of the mass, and what were the velocities after the collision, and how quickly is the bar rotating. We're going to be able to compare our predictions for elastic and inelastic cases with what we actually get for the measurements. We're also going to be able to look at, well, what percentage off are we? And most importantly, and again, this is key, this is saying the initial angular momentum. This is going to give us our final angular momentum after we, actually give the specific numbers. And we're looking for, is this angular momentum being conserved? So for all of our cases, this angular momentum should be conserved. Those values should match. In terms of the energy, well, if it's an inelastic collision, we should expect to get some energy loss. If it's an elastic collision, well, we should get most of the energy staying pretty much the same. Now, right off the bat, I want to make this caveat. We are not going to get any perfectly elastic collisions. We're not going to get any perfectly inelastic collisions. With these objects for the elastic collisions, when I try to make it hit and bounce off, there's always going to be a little bit of energy loss. So again, 10-20% energy losses for the elastic cases. I wouldn't be surprised by any of those. Even when we get the cases where the object sticks to the bar, well, then we should get more energy loss, but again, we're still probably not going to get that perfectly sticks to the bar, because that would have to stick as the bar turns, and these masses are going to be on a track and they're not going to turn as well. So when we're making these comparisons, these ranges for what we would expect to get in the elastic case and the inelastic case for object 1, that kind of gives us a range of we should get somewhere in here for the actual values of our measurements. Again, it's not going to be perfectly one or perfectly the other. Again, I'm trying to make the setups as accurate as I possibly can, but we're not going to get that. Same thing for object 2. We're not going to get these exact numbers, but the number that we do get should be in between these values. But in all of these cases, again, no matter which case we're looking at, this total angular momentum, that one should be conserved. That is our key measurement that we're going to be checking out in this. And also looking at the energy and seeing if, are we getting this massive energy output, or is this a free energy machine that we're making here? A couple other things about these calculations, especially for this one, for the velocity of object 1. These velocities are going to be both small, and some of them might be around 0. And when you're doing the percent difference equation, percent differences with values close to 0, especially when one could be positive and one could be negative, that really throws off these percent differences for these ones. So I would really not trust these percent differences to be very accurate. I'm expecting them to be pretty horrible. These ones over here, at least when we're trying for an elastic case, we should get moderately close. When we're trying for an inelastic case, again, we should get moderately close. But even that, I'm expecting higher percentage errors up here, but in any collision, we should get that total angular momentum equals 0, or total angular momentum is conserved. That's the main thing that I want to kind of emphasize here. When we look at this inelastic case, this is calculating, this calculation, this equation up here is going through and actually plugging in this specific equation. So when we get R1 squared times M1, well, cell B4, that's R1, we square it, times B2, that's M1. Divided by this other combination of terms, you can check it yourself. It should match up with R1 squared times M1 plus R2 squared times M2, that's this term and this term, plus that moment of inertia of the bar, that's cell B6. Okay. Same thing for case 2. Basically, it's the same combination multiplied by R2 over R1. Okay. So those are the predictions from the inelastic case. And these are the predictions from the elastic case. That's this value here. Again, R1 squared times M1 minus R2 squared times this value A. That's cell B4 is squared times this cell minus R2 squared times A, so B7. And then divide by, again, a similar combination of terms. Again, when we're going through this, I'm going to be using the Excel sheet to do these calculations automatically, but don't believe me. Try the calculations yourself. Try plugging the numbers into these equations and making sure that when we're looking at these elastic and inelastic cases, it is actually giving the correct values. For example, right now I have this set up as M1 is twice the mass, but at half the distance, and that matches up with the velocity of object 1 should be negative 1/3 the initial velocity. It should bounce back with a third speed. And V2 should be going at 1.33 times the initial velocity that mass 1 was moving at. If we plug in some of the other cases, so if I do 1s for everything, well, in the elastic case, object 2 should just bounce back, again assuming that there's no bar there, or the bar is a negligible mass. And in elastic case, those two objects should just be kind of, they should each have half the velocity. So again, you can plug in different numbers for this, and this Excel document will automatically update what those predictions are. Okay. So now let's quickly look at the properties of the bar that I'm going to be using. So this carbon fiber bar, this has a mass of 44.6 grams, so let's double check that. So I've got my scale here, put that on top. Okay, looks like it got 0.1 grams since I weighed it last, but again, around 44.6 grams. And this bar is exactly 1 meter long. Again, let me bring this up here. So it's exactly 1 meter long. And I put markers right at the center of the bar, so at the 50 centimeter mark. And then for the half distance, I set another marker up at 25 centimeters away from the center of the bar. And this 1/3 distance, that is 16.7 centimeters from the center of the bar. So this is our fulcrum. This is what we're going to use for our half distance. This is what we're going to use for our full distance. And the other side will always be launching from the very end of the bar. Okay. So if I want to measure the moment of inertia of this bar, well, that's 1/12. If it's a uniform bar, like this is a hollow bar, so this is carbon fiber, it's hollow in the middle, but it's still fairly rigid. It has a little bit of bend. If I start putting some force on it, I can feel a little bit of bend, but hopefully not very much. But we can calculate this total moment of inertia, and this is going to be a very, very small value. And we can input that into our lever predictions, saying, well, this is our moment of inertia of the bar, and when we do that, we're going to get a very, very slight change in our predicted values for how fast we expect this thing to be going in these different cases. So again, we've got those R distances labeled, and again, hopefully this bar is low mass and rigid enough that it, satisfies everyone's requirements. But I did want to make another mention of this wooden dowel that a lot of people objected to because it has a lot more flex in it. Okay? So again, one of the points that I really want to make and test out in this video is that this angular momentum is going to be conserved in all of the cases, even if the bar has some flex to it. That doesn't matter. This total angular momentum will be conserved whenever we have no external torques. And this little flex of the bar, all the little forces that are involved in that flex, those would all produce internal torques. So just so we have the numbers for this one as well, this wooden bar, its mass is right around 59.5 grams. So I'll kind of highlight that one. This bar, the length of this bar, so let me just measure this on here. So first, this is the midpoint of the bar. So I've marked off that midpoint of the bar, so that's the point where it's nice and level. This half of the bar, the total bar is 1.2 meters long. This midpoint, so if I go from here to there, that midpoint of the bar is 60 centimeters. The whole thing is 120 centimeters. This distance adds another 30 centimeters, so this would be my half distance location. This would be my 1/3 distance location, so this is at 20 centimeters. So we can do the same kind of calculations and say, if I use this wooden bar for some of the trials, we can use its moment of inertia as well. Okay? So we are going to add some trials with the flexible wooden bar to see if that has an effect on this conservation of angular momentum. We'll be doing some trials like that. And one last thing that we have to have a look at, or one additional thing, there's going to be a couple more. When we're making these measurements, we not only need to measure the initial velocity of the mass 1 and the velocity of mass 1 and 2 after the collision, we also need to measure the angular velocity of that bar as it rotates. The way we're going to do that is with this little table. When I set up the fulcrums, I'm going to set up the fulcrums so that they're centered on this point right here. So when the object hits the fulcrum, we're going to be able to measure how many degrees does this rotate through in a certain amount of time. Each of these are set up at 10-degree increments, so this is 10 degrees, 20 degrees, 30, 40, 50, 60, 70, 80, and then 90 is just the vertical one there. We're going to be able to measure what is that angular velocity of this system. So that should be all the preamble stuff. So let's switch things up and have a look at our tracks and the levers that we're actually going to use to run this experiment. Okay, so let's have a bit of a look at the experimental setup before we start taking some actual data. Notice I have the carbon fiber bar on this fulcrum point, and notice that that fulcrum point is really low friction. If I give that just a little hit, there's not a lot of friction acting on this bar. It's pretty well balanced, and it is set back a little bit from the very center point. I couldn't actually get the carbon fiber to fit over top of that center point. I don't have any way to drill through carbon fiber, but that little shift in distance is really not any different than if the bar was centered over it and the front face of the bar is a little bit ahead of that fulcrum point. It shouldn't make much of a difference for our data. A couple other things. For the tracks, I've leveled each of the tracks, so hopefully they don't really have any preferred direction. They don't really have any tendency to go in any one particular direction. And every time I move the track, I'm going to make sure I re-level the tracks to make sure that this is as low friction and no tilt of the track that could throw off some of our data. I've also put markers at 10 centimeter intervals on both of the tracks. I'm going to be using the motion sensor data to analyze the motion, but if you want to check those velocities using data from the track, I will put those timestamps on when I show the video of the actual interactions. Also, we've got the side view camera and we've got the top view camera that are going to be recording both aspects of this, and I'm also going to be recording the data that's actually produced by the sensors, the data that's measured by those sensors. So I think those are the main things. Again, we've got the motion sensors on the far ends of the track. Motion sensor 1 is going to be measuring the motion of cart 1 as it goes forward down the track. Motion sensor 2 is going to be measuring the second cart as it is launched by the sensor. Notice that this sensor, the sensor of cart 1, is measuring away from the sensor to be the positive direction. This one is measuring towards the sensor to be the positive direction. And that helps out with the angular momentum calculations, since everything is going around, all that angular motion around this fulcrum point is going to be in that particular direction. So that's going to be what we call our positive direction. We're also going to be looking at different kinds of collisions. So let me move a little bit closer to this camera to identify this. We're going to be trying to make both elastic and inelastic collisions. These are not going to be perfect. There's always going to be, some energy loss or some where it's not completely inelastic, some effects happening there. But for the elastic case, I'm using this, I'm going to hit the end of the track with this spring. I've tried some other methods to make it more elastic. This still seems to be the best one, even though there is definitely some friction on those springs. We do get a little bit of energy loss from that. I'm expecting between maybe 15 or 25%, somewhere in that range for energy loss. But this should be, closer to the elastic case. And when we want to go for the inelastic case, I'm going to flip this around and basically put this clay on the front of the cart. So make a bumper on the front of the cart. So when the cart hits the end of the track or hits the fulcrum, that's going to compress some of that, some of this Play-Doh, and that's going to give us closer to an inelastic collision. So I think those are the main things. If I miss anything, I'll put something in post. But let's get the masses of these carts. So for our first weigh-in, this first case is going to be equal masses at equal distances. So let's get the first weigh-in for the cart. So for cart 1, we are getting a mass of 587.5 grams. 587.5 grams. Well, I've tried to set this up so that our second cart should be pretty much the same. So again, a few tenths of a gram higher, but still pretty much 587.5 for those. So these are equal mass carts. They'll be running into the track at equal distances. So let's get this first setup going. Okay, here we go. So this is going to be equal mass at equal distance, trial number 1 in the elastic case. Let's start taking our data and try the first run. So let's just look at some of the preliminary data for this one. So again, we can identify our initial velocities just before the cart hit and our velocities just after the cart hit. So just before the cart hit, looked like the cart 1 had a velocity of 0.400 meters per second. Cart 2 is basically at rest. And just after the collision, cart 1 was going at 0.02 meters per second, and cart 2 is going at 0.378 meters per second. So that's going to be our first trial for the elastic case, equal mass. Let's reset and give it another try. And then once we do a couple of trials for each of the cases, then we'll go through some of the data analysis for this. And we'll try this again for our next trial. 3, 2, 1. 3, 2, 1. 3, 2, 1. 3, 2, 1. Okay, so looking at our preliminary data, just before the impact, cart 1 was going at 0.479 meters per second, cart 2 basically at rest. After that hit, we've got cart 1 going at 0.007 meters per second, cart 2 going at 0.45 meters per second. And later on, when we get into more of the data analysis, I have to do analysis of the video to figure out, well, how fast was this, was the lever itself moving? So how is that changing our measurements? So we'll be getting into that more when we look at the next set of trials. So I'm going to reset this and set this up for an inelastic case. Okay, got things set up for our next trial, and let's start collecting data. This is equal masses at equal distances in the inelastic case. Again, we'll see how close it is to actually being inelastic, but it's the inelastic, closer to inelastic case. And let's do trial number 1. Okay, let's look at our data. So beforehand, velocity 1 is 0.519 meters per second. Velocity 2 is pretty much 0. Afterwards, velocity 1 is 0.066 meters per second, and velocity 2 is 0.504 meters per second. I'm going to try to get a little bit, try to change this around a little bit more, so maybe we get a little bit more inelastic case. We'll see what we get. And here we go. We've got equal mass, equal distance. This is inelastic case trial number 2. And let's try another data run. Okay, so our preliminary data. Just before the collision, the velocity is, let's go with right there, 0.518 meters per second. Velocity 2 is 0, or 0.002 meters per second. Afterwards, just afterwards, we've got velocity 1 is 0.088 meters per second. Velocity 2 is 0.433. So let's look at the data analysis for the first 4 trials in our data set. And I'm recording these analyses parts a few days after having taken the data, since in order to do this analysis, I had to go through and compile the videos and gather all that data. So you are going to see a back and forth switch between when I recorded the data and when I got a chance to record the analysis part. Hopefully that's not too distracting. But let's look at our first 4 trials. We're going to do this analysis in batches because it would just take too long and be too cumbersome to do the analysis parts after each individual trial. And this is also going to help us be able to more easily compare and contrast similar cases. I'll make sure that I put chapters into the video so you can quickly find where I took the data for each batch of trials and where I did the analysis for each batch of trials. So you can check my work to make sure that I haven't changed any numbers or anything like that. So for these first 4, we've got equal masses at equal distances. And we're going to be checking the video to make sure that we haven't changed anything. So we'll put in the exact masses and the exact r distances, go through and identify what was the velocity of the cart before the collision happened, what were the velocities of the cart after the collision happened, how quickly was the bar rotating. And once we put in that measured data, we're going to be able to compare our model to our actual data. And most importantly, identify whether or not this angular momentum quantity is being satisfied. This angular momentum should always be conserved in cases where there are no external torques acting on our system. Again, the lever itself is quite low friction, the tracks are pretty low friction, so there shouldn't be a lot of external torques happening just before to just after that collision. So in all of these cases, no matter what the specifics of how the collision goes, this angular momentum should be conserved. Okay, that's going to be one of the key things that we're testing. The kinetic energy, well, if I have an elastic collision or something close to an elastic collision, we should hopefully not lose too much kinetic energy. I'm thinking we're probably going to lose a little bit because we're not going to get a perfectly elastic collision. When we use the clay bumper, we're probably going to lose quite a bit more energy. We can check out that prediction. But in no cases should we have an increase in kinetic energy. So those are the things that we're going to be testing. So let's look at this first particular case. So let's look at this first particular trial. And let's look at the specific measurements that we have for this one. So I've set this up so that we can kind of look at the video as well. The masses were both 0.5875 kilograms. And the R distances, the distance from the fulcrum to where the cart hit, in both of those cases were 0.5 meters. And now we can kind of look through our data and say, what was the velocity just before the collision? Looks like this one was 0.400. And our velocity just after the collision, well, for cart 1, it's 0.02, and for cart 2, it's 0.378. Okay? But we also need this angular velocity. Okay? We need a way of measuring what is the angular velocity of this system. So let's go back to this part of the video and see how we're going to measure this, because we are going to use this equation here, saying if I can measure how much of an angle this thing sweeps through in a certain amount of time, I can convert that from an angle in degrees and a time in seconds. I can convert that to this angular velocity in radians per second using this particular equation. So let's look at an example of how this will work. So if we watch the cart hitting that lever, and then I want it to launch the cart, and I want the cart to no longer be in contact, because I want the lever to be at a point where now it's moving at a constant velocity. It's not speeding up, not slowing down anymore. So this lever is just a little bit past the 0 angle mark, and the time is 2.133 seconds. Okay? So let's find out how long it takes to swing through approximately 10 degrees. So if that first time is 2.133 seconds, and let's frame ahead a little bit and say, where does this thing, it's a little bit past the 10 degree mark now. Again, I could be off by a frame or so, but that's not going to change our values all that much. So let's call this one 2.6 seconds. So our first time was 2.133 seconds. This next time is 2.6 seconds. So that's a time difference of 0.467 seconds. So in 0.467 seconds, this thing swung through a 10 degree rotation. So we type in 0.01745 times 10 degrees divided by that time that we just calculated. And when I plug this in, I got 0.374 radians per second. So let's add that in as 0.374 radians per second. Okay? So that will account for how much angular momentum and how much energy that bar is absorbing as it goes through that particular rotation. Couple of things about this measurement. This angular velocity should never be more than the velocity of cart 2 divided by its radial distance, because that would imply that the end of the lever is actually moving faster than the cart, and it would kind of push and ghost its way through the cart. So if we check it in this case, well, V2 is 0.378 meters per second divided by 0.5 for that radial distance. Well, I got 0.756 would be the maximum angular velocity of that bar. And note that the bar is about halfway behind the cart at this particular point. So this angular velocity we're getting is about half of that maximum value, that 0.756. Okay? So again, there are ways that we can check this. There are ways that we can measure this using our data. I'm not going to do this measurement for each and every one of the trials because that will take forever. I've actually gone through these videos and measured all of these angular velocities, but you are always have the opportunity to check my work, make sure I'm not too far off, and we're actually going to see how far off, if I change some of these values, how far off does that make my results. Okay, well, I've been hiding the calculations, so let's see how the calculations compare for this first trial. Okay. Well, these percent differences, since we're measuring velocities that are so close to zero, these percent differences, especially for the for what cart 1 is doing after the collision, are going to be very, very high. Okay, so again, I kind of put down here that we're expecting high errors for these values. But in this case, well, we were expecting a velocity of, this comparative velocity of 0.987. We got 0.945. We were only 4% off. More importantly, this angular velocity was only off by 0.7%. That's actually more accurate than I'm expecting to get in most of these cases, but it sure is a good start. Okay. And in terms of the kinetic energy, well, we lost a little bit of kinetic energy. Even with these springs, I'm expecting to lose, 10, 20, maybe 25% of the energy. But that's kind of in the ballpark of what we're expecting. Okay. So in this first case, our angular momentum was conserved, and our kinetic energy for the spring bumpers was pretty much conserved. So again, I'm going to go through the next couple trials more quickly. I've already compiled the data for these ones. And for the second trial, again, we had the same masses, same r distances, and the initial velocity was 0.479. Velocity of cart 1 after the collision was 0.007, basically 0. And the velocity of cart 2 was 0.45. And since this was rotating a little bit faster, this angular velocity was 0.522. Once again, when measuring this angular this angular momentum, we were only 3% off between our initial and our final angular momentas. Energy, again, we were using the spring bumpers again, so that was almost conserved. Once again, these numbers in here are going to be very high percent errors just because these velocities are so small and they're actually straddling around zero. So that's kind of an artifact of how this percent difference calculation works. But when we look at cart 2, we see that, well, we matched pretty well. What about for the cases where we use clay? So we're still using equal mass and equal distance. For trial number 3, the initial velocity was 0.591. Velocity of cart 1 after the collision was 0.066. Velocity of cart 2 after the collision was 0.504. And I measured the angular velocity of the bar to be 0.582. Well, once again, our angular momentum within 2% of each other, 2.5% of each other. And in this case, since we were using the clay bumper, well, more kinetic energy was lost. The thing still bounced off of that clay bumper, so again, we're still not very close to that percent difference in the inelastic case, but we did lose more energy in this case, regardless of the fact that our angular momentum was still being conserved. One thing that we're going to be wanting to check for is that in all of these cases, we have our prediction for the ratios of velocities of cart 1 and cart 2 compared to the original velocity in the elastic case, the perfectly elastic case, and the perfectly inelastic case. Those give us a range where we expect our actual data to fit in. Like I said, based on the equipment that I have, we're not going to get any perfectly elastic collisions, and we're not going to get any perfectly inelastic collisions. The clay still has a little bit of bounce to it. It didn't really stick to the cart. I'm thinking of some ways for future experiments to kind of make that a little bit better, but it does still give us a range of plausibility. These measurements, again, are inside of that range, whether we're using the clay bumpers or whether we're using the springs. But let's also look at trial number 4. So trial 4 was also using the clay, and the initial velocity for trial 4 was 0.518. Final velocity for trial 4 for cart 1 was 0.088. For cart 2 is 0.433. And the angular velocity of the bar that I measured was 0.477. Once again, we get excellent agreement with the angular momentum. And in this case, well, again, we're using clay, so more of the kinetic energy is being lost than when we had the spring bumpers being used. Our measured velocities, or those ratios of final to starting velocities, are again within the ranges that we expect. Okay. So this data looks pretty good so far, but again, this was in the equal mass, equal distance case. And with just this equal mass and equal distance case, we might actually start to see a signal that might look promising but is actually false. You might say that from this data, if I were to just do the mass of 1 times the velocity of object 1, and then take that and compare it with the mass of object 1 times the velocity of 1 after the collision, mass of 2 times the velocity 2 after the collision, when you add those up, you'll get something that matches pretty accurately. And that might lead you to think that linear momentum is being conserved in this case. It's still not being conserved, because linear momentum, as we've demonstrated before, linear momentum has a direction to it. When the original cart is going in to the camera's left, well, it's moving in a particular direction. That cart basically stops and it launches the other cart in the opposite direction. If that other cart is moving in the opposite direction, that is a different momentum. Momentum has direction. We can't just say those momentas, the magnitudes of those momentas are going to be equal, because when we're using conservation of momentum, the direction matters. And also, when we get into more cases where R1 and R2 are not the same, we're going to see that this model of momentum, trying to use conservation of momentum or conservation of the magnitudes of momentas, is going to fail. So we'll see that in some of the next cases where we have different masses and hitting different points on the bar. So let's look at those next. Okay, so I've moved the tracks in, so now this cart is going to be twice the mass, hitting at half the distance. So this was our half distance location. That's where it's going to be hitting the lever, and we've got twice the mass. So again, I've leveled the track. It's not accelerating in any one direction or the other. So let's do the weigh-in. So for this weigh-in, again, I've adjusted the amount of Play-Doh that I'm using on here, and cart 2 has a mass of 291 grams, and if we switch over to cart 1, this is double the mass, and I adjusted this so it's exactly 582 grams, exactly twice 291. So we've got those two masses, and let me set this up for our next data run. Okay, here we go. So this is double the mass at half the distance. We're doing the elastic case first, so this is elastic trial 1, and let's go. Okay, so notice on this one, in the elastic case, we got this bounce back. And let's look at the preliminary data. So just before the collision, as close before the collision as we can get, velocity 1 is 0.468 meters per second. Velocity 2 is essentially 0. Afterwards, well, now we've got velocity 1 is rebounding in the opposite direction at negative 0.114 meters per second. Velocity 2 is 0.548 meters per second. So that's our first data run, but let's do another trial. Okay, so this is trial 2, double mass at half distance, elastic case, and let's see what we get. Okay, so let's look at the preliminary data. Just before the collision, velocity 1 is 0.477 meters per second. Velocity 2 is essentially 0. After the collision, cart 1 rebounds back with a velocity of negative 0.131 meters per second. Velocity 2 is 0.571 meters per second. Okay, so that was trial 2 of the elastic case. We're going to switch things over, and I'm going to set this up for the inelastic case. Okay, so this is double mass at half distance, the inelastic case, trial number 1. So let's see what we get here. Okay, so just after the collision, we've got a velocity 1 of 0.596 meters per second. Velocity 2 is essentially 0. And here we've got velocity 1. Where do we want to find that one? We'll go with this one. Just barely bounces back with a velocity of negative 0.005 meters per second. Velocity 2 is 0.559 meters per second. So let's reset this. Okay, so this is double mass at half distance, trial number 2 in the inelastic case. And let's take some data. Okay, let's see how this one worked. So, just before the collision, velocity 1 is 0.667 meters per second. Velocity 2 is, again, essentially 0. Just after the collision, okay, we'll call that one the one right after the collision. Velocity 1 is 0.056 meters per second. Velocity 2 is 0.564 meters per second. Okay. So again, those were the inelastic and elastic cases for the half mass at double the distance. We are definitely not getting the cart bouncing off the end going, ridiculously faster than the first cart, but let's see what we get for the analysis. So let's look at this next set of trials. So for trials 5, 6, 7, and 8, we've got double the mass hitting at half the distance. So I've already gone through and put in the masses of the two carts, the R distances, the distance from the lever, the fulcrum point for each of those. And for trial number 5, if we put these numbers in, the measurements were the original velocity of the cart was 0.468 meters per second. The velocity of cart 1 after was negative 0.114. And the negative, again, just means instead of kind of hitting and going through, it bounced backwards from its original direction. Velocity 2 is 0.548, and the angular velocity of the bar that I measured was 0.873 radians per second. Okay. Now, just to kind of review this measurement of the angular velocity of the bar, remember, we have this equation saying if I know how many degrees it rotates through in a certain amount of time, we can measure what that angular velocity is. So let's redo this, this calculation real quick. And if I look at this part of the video, The cart hits and launches cart number 2. And let's use this as our first reference point. The lever is no longer in contact with the cart, so it's not going to be speeding up or slowing down anymore from there. And it's just before the 10-degree mark. Okay? And the time is 2.266 seconds. If we frame ahead a little bit, then at 2.466 seconds, well, the lever is just behind the 20-degree mark. So that means it's gone 10 degrees in 0.2 seconds. So with this equation, if we have 0.01745 times 10 degrees is how much it rotated, divided by that 0.2 seconds, that gives us the 0.875 that we have for this angular velocity measurement. And notice that, well, our angular momentum matched to within 2.5%. You know, we did lose a bit of energy, and as we were expecting, you know, even using the spring bumpers, we are going to lose a fair amount of energy. But notice that for these velocity ratios, what we got was not far off from the elastic case. And again, it's within that range that we're expecting. Same for cart 1. It's not exactly what we were expecting for the elastic case, but it is in the valid range that we were looking at. So this one looks pretty good. Let's look at the next one. So for trial 6, the original velocity before the collision was 0.477. Velocity of cart 1 after was negative 0.131. Velocity of cart 2 was 0.571. And the angular velocity was 0.656 radians per second. Once again, our expected ratio of velocities for cart 2, reasonably close match. Pretty good match, less than 5% for the angular momentum. Angular momentum is being conserved, and we're getting a similar amount of energy loss, around 20% energy loss, which, again, is more than is ideal for an elastic collision. But like I said, these spring bumpers do have a little bit of friction acting on them. We do expect some energy loss. However, for the next set of trials, we should, since we're using the clay, we should still have the conservation of angular momentum, but there should be significantly more energy loss when we're using the clay. So trial 7 with clay bumper, double mass, half distance. The velocity before the collision was 0.596. Velocity after was negative 0.005 for cart 1. For cart 2, 0.559 meters per second. And the angular velocity of the bar, 0.873. And once again, we get this matching angular velocity. Our measured velocities ratios for the individual carts are in the expected ranges. Again, these percent errors are a little bit higher because we didn't get completely inelastic. We did not get perfectly elastic. We got somewhere in between those. But angular momentum was conserved, and we got more energy loss because we were using the clay in this case. One other thing I wanted to mention about these angular velocity measurements is because the moment of inertia of the bar is very, very low, these angular velocity measurements aren't going to throw off our angular momentum or our total energy very much. So we said this value should be 0.873. If I went down to, like, say, 0.7, a significant change, it doesn't change our percentages very much from what we had before. If I overestimated it, let's call it 1, for example, well, we still get pretty similar scales for how far off it throws our angular momentum measurements and our energy measurements. Again, that is because we've got a very low mass bar, a bar with a very low moment of inertia. We could redo this experiment with other bars or other objects with larger moments of inertia, and this would be another way that we could calculate, that we could test out some of these ideas with conservation of angular momentum. But let's look at trial 8. So for trial 8, it was also clay, so the initial velocity before the collision was 0.677. Velocity of cart 1 after was 0.056. Velocity of cart 2 was 564 meters per second. And the angular velocity, this one was going a little bit faster afterwards. Once again, angular momentum being conserved. But in this case, we're getting more energy loss because we're using those clay bumpers. But in all of these cases, we should expect conservation of angular momentum. So far, all this data is looking good. But let's go on to the next set of trials. Okay, for this next set, we're looking at the 3 times the mass at 1/3 the distance. So I have again leveled the tracks, made sure that they're exactly as close as I can get parallel to each other, and now we're hitting at the 1/3 distance. So this is at 16.67 centimeters. This one is at 50 centimeters. So let's do the weigh-in for these carts. So again, cart number 2, we still have that cart empty, so that should still be around 291 grams. So 3 times 291, with all that stuff on it, should be 873. We're a few tenths of a gram over, but again, close enough, well within 1%, actually within like 0.1% off for the masses for those. So again, we've got 3 times the mass versus 1 times the mass, the original mass. And let's get this set up. So again, we're going to start with the elastic case. So let me just get everything nicely aligned on here. So this is 3 times the mass at 1/3 the distance, elastic trial 1. So here we go. Okay. And if we look at the initial data for this one, well, the initial velocity was, for cart 1, was 0.536 meters per second. Afterwards, well, we definitely didn't get 3 times the velocity, but let's see what we did get. Cart 1 is bouncing backwards at 0.227 meters per second. Cart 1 is going at 0.689 meters per second. Okay, and let's reset for another trial. Okay, so this is 3 times the mass at 1/3 the distance, elastic case, trial number 2. Let's take some data. Okay, and for this trial, velocity just before impact was 0.547 meters per second for the original velocity. Cart 2 is at rest. And just after, go with that point, just after the velocity of cart 1 is bouncing back at negative 0.229 meters per second, cart 1 0.693 meters per second. And we will switch over to the inelastic case. Okay, so this is the 3 times the mass, 1/3 the distance, the inelastic case, trial number 1, and let's start taking some data. So, for this data run, just before the collision, the velocity is 0.634 meters per second. Just after the collision, cart 1 has a velocity of negative 0.057 meters per second. Again, this isn't as inelastic as I was hoping it would be, but this should have less conservation of energy than the other one did, but the conservation of angular momentum should be the same. We'll see what we get in the analysis. So cart 1 is bouncing back at negative 0.057 meters per second, and velocity of cart 2 is 0.646 meters per second. Let's reset and try one more trial. And let's give this a try. So this is 3 times the mass, 1/3 the distance, inelastic case, trial number 2. like we're getting something pretty similar to last time, but let's go through the numbers. So velocity of cart 1 is 0.493 before the collision. After the collision, velocity 1 is negative 0.025 meters per second. Velocity 2 is 0.486 meters per second. And then we'll go into the analysis for these. Okay, so for this next set, we've got triple the mass at a third the distance, 2 with springs and 2 with clay bumpers. So we've got masses 1, mass 2, R1, R2, moment of inertia of the bar, and let's just jump right into looking at some of these cases. So trial 9, the velocity before the collision was 0.531, velocity 1 after was negative 0.227, velocity 2 after is 0.689, and the angular velocity that I measured in that case was 1.16. And when we run through that, well, let's look at our numbers. Well, our angular momentum was only off by just under 8%, so a little bit higher error in this case, but since we're measuring these R values to be a little bit smaller, it's going to be a little bit more sensitive to errors. We still have around 20% energy loss, even though we're using the spring bumpers, but again, we're expecting those kinds of energy losses for our cases. But once again, our measured velocity ratios all within the expected ranges and closer to the elastic cases in these. So looking pretty good for that one. Trial number 10, also using the spring bumper. This one, the initial velocity was 0.547. After, cart 1 had a velocity of negative 0.227. Cart 2 had a velocity of 0.693, and the angular velocity is 1.05. Well, this one seems to be the highest error yet. So the angular momentum is off by about 10%, but we're still getting a similar value for the energy. So a little bit of energy loss. And again, our measured velocity ratios are inside of the expected ranges. Again, both closer to the elastic cases. Now notice, let's say I measured this R1 distance to be off a little bit. Well, I can change that a little bit and see, well, how much would that affect my percent difference? And in this case, since this R1 value is kind of small, let's say I just went to 15 centimeters. That actually throws our numbers off quite a bit, or if I went to 18 centimeters, well, it throws our numbers off quite a bit more. So I suspect that this is part of the reason why we're getting a little bit higher percent errors, just because since we're measuring the mass being a little bit closer to the bar, we're a little bit more sensitive to errors in measuring that distance accurately. But the things to point out are we're still getting a pretty decent agreement between the initial and final angular momentas. And in terms of the energy, we're still getting a similar energy loss. We are not getting an increase in energy for any of these cases so far. What about using the clay bumpers? So this was trial 11. So for trial 11, the initial velocity was 0.634. Final velocity of cart 1 was negative 0.057. Cart 2 is 0.646, and that angular velocity was 1.31. Well, looks like for this one, we got really close for that angular momentum. And notice we're losing a lot more energy in this clay example. Just because we're losing energy doesn't mean this system can't conserve angular momentum. And once again, our velocity ratios are inside of those expected ranges. Not very close to either the elastic or inelastic cases, but they're inside of those valid ranges. And that's what we really care about because, again, we don't expect that these trials are going to be perfectly elastic or completely inelastic. It's just going to be inside of that particular range. So trial 12, let's put this one in. So 0.493 meters per second is the velocity before the collision. After the collision, cart 1 had a velocity of negative 0.025. Cart 2 is 0.486 meters per second, and the angular velocity is 0.749. Once again, angular velocities match. It's closer to an inelastic collision since it's clay, so a lot of energy loss, but our velocity ratios are inside of the expected ranges. So notice, in none of these cases with the triple the mass at a third the distance are we getting any sign whatsoever that we're producing energy, that we have some free energy machine here. All of it is determined by this conservation of angular momentum, and then whether we have an elastic or inelastic collision determining how much energy is conserved. Those are the physical principles that are governing this lever system. Notice, if you put in linear momentum, if you try to put in linear momentum with these different masses, you will get very, very different results. Linear momentum is not conserved because there's an external force at the fulcrum. Wherever we have that fulcrum point, when the cart's hit, there's an external force acting on that. But around that fulcrum point, there are minimal external torques, which means these angular momentas are going to be very close to being conserved. So let's look at some cases where we don't have these nice balanced systems where it's double the mass at half the distance or triple the mass at a third the distance, because this should work for any combination of masses and distances. So let's look at those trials first.
So one of the things that I also wanted to test out was the fact that we don't have to have one of these nice ratios of twice the mass at half the distance or 3 times the mass at a third the distance. We can use any combination of masses that we want, and we still should get this conservation of angular momentum. That property should be independent of what things I'm throwing at what locations on the bar. So we're going to test out a couple of examples. So for this first example, I'm going to do equal masses, but the cart that I'm throwing, it's going to be at half the distance. So equal masses, but the cart being thrown is at half the distance. So let's do the weigh-in procedure for this. So again, in this case, we should have equal masses. This is cart number 2. It is right around 583 grams, just shy of that. And this is cart 1 with the stuff that I put on top. It should be same thing, 582.8. I've, again, tried to dial in these masses as closely as possible. So let's try this setup. So let me just get everything nicely arranged. Okay, everything is now aligned. So again, this is equal mass, but cart 1 is hitting at half the distance that cart 2 is being launched at. So let's start taking some data. And this is the elastic case trial 1. So here we go. All right, so let's see what we got here. Just before the collision, cart 1 was traveling at a speed of 0.554 meters per second. Just after the collision, well, velocity 1 is negative 0.282 meters per second. It bounced back. And velocity 2 is 0.408 meters per second. So that's trial 1. Let's save that and give it another trial. So this is equal mass hitting at half the distance, trial number 2, and here we go. So velocity 1 is 0.415 meters per second. Velocity 2, velocity 1 bounces back at negative 0.199 meters per second. Velocity 2 is 0.308 meters per second. Let's try this in the inelastic case as well. Okay, so this is equal mass hitting at half the distance in the inelastic case trial 1. So let's start collecting some data. Just before the collision, velocity 1 was 0.641 meters per second. Just after the collision, velocity of cart 1 was bouncing back with negative 0.145 meters per second. Cart 2 was launched at 0.382 meters per second. And let's set this up one more time. So this is equal mass, half distance hit, inelastic case, trial number 2. So let's start taking data. Okay, so just before the trial, the initial velocity was 0.526 meters per second. Just after, velocity 1 is negative 0.116 meters per second. Again, this is definitely not completely inelastic because it does still bounce off. It didn't stick to the side, but we'll see if it's closer to the inelastic case. So velocity 1 is negative 0.116 meters per second. Velocity 2 is 0.314 meters per second. And let's analyze some of this data and see if we get that conservation of angular momentum even in these cases.
So trials 13 to 16 are equal mass, but at half the distance. Cart 1 is hitting at half the distance of cart 2. So this is not one of the balanced cases, but a more general case. So we've got the masses in there are both 0.583. R1 is 0.25 meters, R2 is 0.5 meters. And let's look at trial 1. Trial 1, the initial velocity before the collision was 0.554. Object 1 bounces back after, and that velocity is negative 0.282. Velocity of cart 2 is 0.408, and the angular velocity of the bar is 0.524 radians per second. Once again, we get a very close match between our initial and final angular momentas, off by just over 1%. And again, a moderate loss of energy due to these springs, but similar to what we've been seeing in all of the other cases. Our velocity ratios are inside the expected ranges and actually pretty close to what we expect from this elastic case. Again, these percent differences in elastic, this is the elastic case, so those don't really apply. Let's look at trial 14. This is also using the spring bumper, so for 14, the initial velocity was 0.415 meters per second. Velocity of cart 1 after was negative 0.199. Velocity to cart 2 was 0.308. Angular velocity was 0.374. Once again, same angular velocity, angular momentum. So the angular momentum was conserved to within 3%, similar amount of energy loss, and again, our velocity ratios are inside the expected ranges. Trial 15, this was doing the same thing, equal mass, half distance, but using the clay bumper, so there should be more than 20% energy loss. This should be a marked increase in the energy loss. So initial velocity is 0.641 before the collision. Cart 1 after is negative 0.145. Cart 2 after is 0.382. And the angular velocity of the bar is 0.477, what I measured for that one. Again, any of these numbers you can check. You can check my angular velocity measurements. You can check any of these percent difference calculations. Use this conservation of angular momentum. We're just using Excel to speed things up. Once again, angular momentum matches before and after. Only 1.5% off. And now, since we were using a clay, now there is a significant loss in kinetic energy for the system. Notice our velocity ratios are still inside the expected ranges, but this time they're a little bit closer to the elastic cases. Again, these percent differences are highly exaggerated because it's kind of straddling zero, and that throws off this percent difference calculation. But again, they're still in the expected ranges. We're not getting perfectly elastic or completely inelastic collisions. We're getting somewhere in between, which is what we're matching with our data. Trial 16, another trial of the same sort of thing. Velocity before the collision, 0.526 meters per second. Velocity of cart 1 after is negative 0.116 meters per second. Velocity of cart 2, 0.314. And the angular velocity is 0.349 radians per second. Matching angular momentas and a similar energy loss velocity ratios in the expected ranges. Again, all of this supports the classical understanding, the textbook understanding of physics, that this system is governed by conservation of angular momentum primarily, and then whether energy is conserved or not depends on what kind of bumper it's running into. And in no cases do we get an increase in energy. There's no free energy here. Let's do the next set of trials.
So for this set, we're again going to look at a different mass and distance combination. We're going to have equal distances, but this cart has twice the mass. So let's do the weigh-in procedure. So this cart, just again on its own, is 291 grams. This one should be double that at 500, right at 582 grams. So we've got double the mass, but we're hitting them at the exact same distance. So let's get this set up. Okay, so this is twice the mass at the same distance, so twice the mass at an equal distance. This is the elastic case. And let's take our data. So here we go. 3, 2, 1. Okay, so for this first trial, velocity 1 is 0.500 meters per second. And afterwards, go there. The velocity of cart 1 is 0.18 meters per second. Velocity 2 is 0.587 meters per second. So that is trial 1 for twice the mass at equal distance in the elastic case. So again, we've got twice the mass, equal distance hit. And we've got the elastic case trial number 2. And let's start taking some data. So for this one, getting pretty consistent in my throws, velocity 1 is 0.526 meters per second before the collision. After the collision, velocity 1 is 0.187 meters per second. Velocity 2 is 0.625 meters per second. And let's reset for the inelastic case. Okay, this is double the mass, equal distance, inelastic case, trial number 1. And let's take some data. For this one, we've got velocity 1 is 0.624 meters per second. After the collision, velocity 1 goes down to 0.248 meters per second. Velocity 2 is 0.691 meters per second. And we'll reset. Okay, so this is double the mass, equal distance, inelastic case, trial number 2. So here we go. Velocity 1 is 0.603 meters per second. That's before the collision. After the collision, velocity 1 is 0.245 meters per second. Velocity 2 is 0.663 meters per second. So, let's analyze this data.
Okay, next set. Trials 17 to 20 are double the mass at equal distances. So again, we got the masses in there. We've got both distances as 0.5 meters. And let's run through the trials. So trial 17, this was with a spring. Initial velocity before the collision was 0.5. After the collision, object 1 was moving at 0.18 meters per second. Object 2 was moving at 0.587 meters per second. Angular velocity was 0.749 radians per second squared. Once again, no significant change in the angular momentum. And in this elastic case, we have minimal energy loss, velocity ratios inside the accepted ranges. Next trial, trial 18. Initial velocity before the collision was 0.526 meters per second. After, cart 1 is 0.187. Cart 2 is 0.625 meters per second. And the angular velocity is 0.873 radians per second. Once again, total angular momentum pretty much conserved, and minimal energy loss since it's an elastic case. When we change to the clay bumpers, this is trial number 19. The initial velocity in the x direction was 0.624 meters per second. Cart 1 after is 0.248, and cart 2 after is 0.691 meters per second. Angular velocity of 0.873. A couple of these were 0.873. And notice in this case, well, we still have a match with the angular velocities. We don't actually get very much additional energy loss, because in this case, even if I sub in like this completely inelastic collision, just based on the fact that we've got a lot of mass moving to begin with, it's not kind of anchored at a closer in point. It's not going to change its motion as much. Even in a perfectly inelastic case, we wouldn't lose that much energy. But we did lose a little bit more than in the elastic case. Trial 20. Initial velocity before the collision, 0.603 meters per second. Cart 1 after is 0.245 meters per second. Cart 2 after is 0.663. And the angular velocity, again, is around 0.873. Once again, close match with the angular momentas. A little bit more energy loss from when the elastic cases for the same ones. Velocity ratios in the same area. Even though we have these different masses and different R values, we're still getting this conservation of angular momentum, and conservation of energy depends on what type of collision we're dealing with. Let's look at the next set of cases.
So for these next couple of trials, I've switched out the carbon fiber bar for this wooden dowel, because when I kind of posted some preliminary trials, just kind of as a preview, a lot of people were kind of wondering about the flex of the bar. And what I want to demonstrate is that as far as conservation of angular momentum is conserved, the flex of the bar really doesn't matter. It might affect how close we're getting to an elastic collision or an inelastic collision, but as far as angular momentum is concerned, all we really care about is, are there any external torques acting on this system? So I've set up this bar. Again, it's fairly well balanced. It's got fairly low friction. If I give it a little push, moves pretty well. We're nice and centered. And the first trial that we're going to do, notice these are again leveled. The first trial we're going to do is the twice the mass at half the distance. So let's do the weigh-in for these. So again, this is the target cart first. Cart 2 is going to have a mass of 291 grams. And this one should be pretty close to double that, within a few tenths of a gram of double that, 582 grams. So we've got the masses. So let's set up the trial. So this is a flexible bar, twice the mass at half the distance. We're just going to look at the elastic cases for this one, and let's start taking some data. Here's trial 1. So we'll ignore that weird spike in there. Let's zoom in on just this data. So if we look at this section of data, just before the collision, our velocity is 0.615 meters per second. After the collision, Cart 1's velocity is negative 0.111 meters per second, and Cart 2 has a velocity of 0.69 meters per second. So let's try another run for that. Okay, so this is a wooden bar, twice the mass at half the distance, elastic collision, trial number 2. Let's take some data. Okay, so for this trial, if we scale this one, just before the collision, our velocity is 0.53 meters per second, so the initial velocity. After the collision, Cart 1 has a velocity, it bounced back, has a velocity of negative 0.093 meters per second. Cart 2 has a velocity of 0.587 meters per second. Okay, so we're going to change this around. I'm going to change up one or two more mass configurations and position configurations, but let's look at the data for this one first.
So for this next set, we are looking specifically at the wooden bar now. So instead of a rigid bar, we have a flexible bar. And since we're now using the flexible bar, the wooden one, we have to change the moment of inertia. So I've updated that, I've put the masses in, and let's go through some of these trials. So this was twice the mass at half the distance. Let's see if the fact that the bar has some flex to it actually does change something about this conservation of angular momentum. So trial 21, original velocity before the collision was 0.615 meters per second. After the collision, object 1 bounced back with a velocity of 0.11 meters per second. Cart 2 after is moving at 0.690 meters per second, and that angular velocity in that case was 0.746. Once again, angular momentas match up, so angular momentum is conserved, and in this case the bar seems to be losing a little bit more energy than we had for the rigid bar. But again, our velocity ratios are still inside the expected ranges from a perfectly elastic to a completely inelastic case. So again, angular momentum conserved. Trial 22, same sort of thing. In this case, the initial velocity before the collision was 0.530. After, object 1 had a velocity of negative 0.093 meters per second. Velocity 2 is 0.587 meters per second. Angular velocity is 0.656 radians per second. Once again, angular momentas match up, and we get a similar amount of energy loss, and our velocity ratios are, again, inside of those expected ranges. So, at least for this case, the fact that the one bar was flexible doesn't seem to have significantly affected the conservation of angular momentum in any way. Oh, let me undo that. It doesn't seem to have affected the conservation of angular momentum in any way, and it just, again, is another factor of whether energy is conserved or not, but we are still definitely not increasing the energy of the system. Let's look at the next trial.
Okay, for this one, we're going to go with the 3 times the mass at 1/3 the distance, again, using the flexible rod. So let's have a look at this. Let's do the weigh-in for these. So again, this is cart number 2. This is going to be your lower mass cart, the 291 grams. And I've loaded this one back up. So that should be exactly 3 times as much, 873 grams with all that stuff on it. So let's set this up. And okay, so this is 3 times the mass at 1/3 the distance. Flexible bar, elastic collision, trial 1. Let's give this a shot. Okay, so just before the collision, the initial velocity was 0.524 meters per second. Just after, the cart 1 bounced back with a velocity of negative 0.176 meters per second. Velocity of cart 2 was 0.633 meters per second. Okay, so we've got that last one, and let's reset and do one more trial. So this is 3 times the mass, 1/3 the distance, wooden bar, elastic collision, trial 2. So for this one, we've got the velocity just before the collision is 0.456 meters per second. The velocity of cart 1 just after the collision is negative 0.168 meters per second. Velocity of cart 2 is 0.579. So we're going to save that, and then let's look at some of the analysis to again see what's happening with the angular momentum.
Okay, we're still using the wooden bar, so we're still using that moment of inertia, but now we've got triple the mass at 1/3 the distance, and let's go through some of our trials. So trial 23, initial velocity was 0.524 meters per second. Velocity of cart 1 after is negative 0.176 meters per second. Velocity 2 after is 0.633. And our angular velocity for that case is 0.873. Once again, angular momentum is conserved. We have a similar amount of energy loss. Our velocity ratios are, again, inside those expected ranges. So, again, we did not get any sort of violation of this conservation of angular momentum. We didn't produce any free energy from this case. But let's look at trial 24. So, same case, wooden lever, spring bumper, triple the mass at 1/3 the distance. Trial 24, initial velocity is 0.456 meters per second. After cart 1 is moving at 0.168 meters per second. Cart 2 at 0.579 meters per second. And the angular velocity is 0.873. Once again, angular momentas match and a moderate loss of energy, velocity ratios inside of those expected ranges. So again, our flexible bar doesn't seem to have changed any of these results. Let's look at our last trial.
Okay, so this one we're going to try a non kind of quote unquote balanced one where I have equal masses where the one that's hitting is starting at half the distance. So let's do the weigh-in first. So again, these should be equal masses. So cart 1, I've left that the same, should still be 582, so pretty close to 582. This cart, again, within a few tenths of a gram of each other. These are, to high accuracy, the same mass for the carts. And let's get the video set up. Okay, so again, this is wooden lever, equal masses, hitting at half the distance, elastic collision, trial 1. Let's give this a shot. Okay, so when we look at these, before the collision, our velocity is 0.463 meters per second. After, cart 1 has bounced back, going negative 0.172 meters per second. Cart 2 is moving at 0.325 meters per second. So that's going to be our trial 1 for this one. Okay, so this is wooden flexible lever, equal masses, hitting at half the distance, elastic, trial number 2. So let's take the data. Okay, so for this trial, velocity before the collision is 0.586 meters per second. After the collision, cart 1 bounced back and has a velocity of negative 0.239 meters per second. Velocity 2 is 0.414 meters per second. And let's analyze this data to again see if the angular momentum is conserved in these cases.
So, this last set of cases, we're still using the wooden lever, so we're still using its moment of inertia, but we've got another one of these unbalanced cases where we've got equal masses, but object 1 is hitting at half the distance. So, let's do this last test of making sure conservation of angular momentum is still holding accurate. So, for trial 25, the initial velocity before the collision is 0.463 meters per second. Velocity 1 is negative 0.172 meters per second. Velocity 2 is 0.325 meters per second after the collision. And the angular velocity of the bar for this one was 0.228 radians per second. And when we look at this, well, this one there must be some source of error here because the angular momentum is actually increasing a little bit, but again, not very much. This is still kind of in the realm of noise. But still pretty good match for that. Energy is still decreasing, and our velocity ratios are still in these expected ranges. So that one seems to match up, again, with expectations. And let's look at trial 26. So in trial 26, the initial velocity is 0.586 meters per second. Velocity 1 after the collision is 0.239 meters per second. Velocity 2 after is 0.414, and the angular velocity is 0.262. Again, something might have been off with the balance of the tracks because, again, we're getting a little bit of an increase in angular momentum, but, again, pretty much still within the noise. Still in agreement to within just a few percent. Still get a similar amount of energy loss, and our velocity ratios are one last time in the ranges that we expect. So what did we learn here? We performed 26 trials on lever systems covering 13 different physical configurations. We demonstrated that it is the angular momentum, this angular momentum value, that is of key importance when considering the motion of these kinds of lever systems. Whenever we have a system where there are no external torques, angular momentum will be conserved. This is covered in any intro physics textbook, and it does apply to these lever cases. It doesn't matter whether we use springs for the bumper or whether we use clay for the bumper. It doesn't matter whether we use different masses thrown at different distances. It doesn't matter whether the bar has some flex to it. In all of these cases, when we measure the initial angular momentum and the final angular momentum, we find very, very close agreement, again, in all of these different cases. As long as there is no external torque applied to this system, the angular momentum is going to be conserved, and that matched the data that we got. Again, this isn't just a claim. This is experimentally verified with these trials to a high degree of accuracy. Of the 26 trials that we did, the initial and final angular momenta matched to within 5% for, again, 22 of those 26 trials. And a full half of the trials had those initial and final angular momentas matching to within 2.5%. There was only a single trial where the initial and final angular momentas were off by more than 10%, and it was just over 10%, and that was the case where the cart was very, very close to the lever, so it was very, very sensitive to small changes in that position. In each and every case that we looked at, the measured final velocities of carts 1 and 2 were within the expected ranges between the perfectly elastic case and the completely inelastic cases, as predicted by standard physics principles. In every scenario where we used both spring bumpers and clay bumpers, where we did the same kind of setup, but just changing which bumpers we were using the spring bumpers got us closer to the elastic case. So if we go to some of these cases over here, using the spring bumpers, we were a lot closer to the elastic case. Using the clay bumpers, we were a lot closer to the inelastic case. Not super close because it didn't hit and stick completely to the cart, but we did get a lot closer. There were 0 cases where we saw any increase in energy from the system. Even when we had these cases where I'm throwing a high mass object closer to the fulcrum point, so the 3 times the mass at 1/3 the distance, we did not see any evidence whatsoever for an increase in kinetic energy. Linear momentum is also not conserved in these lever systems because there is an external force at the fulcrum point, and the linear momentum of a system is only conserved when there are no external forces. This is what makes a model scientific. The standard physics principles that you learn about in any physics textbook or any intro physics course, things like Newton's laws, conservation of energy, conservation of momentum, conservation of angular momentum, and a whole bunch of others. These principles, when properly understood and properly applied, allow us to build predictive models of how physical systems will behave so we can make testable predictions for experiments and observations. We keep the principles that survive repeated testing, and we discard those that do not hold up to scrutiny. In these experiments, we have demonstrated, again, not claimed, but demonstrated, that angular momentum accurately describes the behavior of these systems, as well as conservation of energy in the elastic cases. Again, if I go to more of the elastic cases, we were much closer to having this energy conservation. So these principles of angular momentum and conservation of energy, those are ones to keep. Conversely, we have demonstrated that these levers do not violate conservation of energy. So that idea can be safely discarded. So I hope that this was interesting. This one did take a lot of work, and I know that this is very, very long. Thank you if you watched through the entire thing, or if you just watched through part of it, thank you as well. As always, I try to answer questions in the comments. When you're answering questions in the comments, please try to be respectful and courteous to others. And again, thank you for watching, and we'll see you in the next video.